of section 9.2. So 9.2 deals with vectors. How many have seen vectors in another class, like a physics class or a science class? How many have seen those? Okay, Mario's seen them, and so vectors are used to represent forces and velocities in space. That's one of their big things, right? So a vector has a direction and a magnitude. That's what defines a vector. So forces and velocities also have directions and magnitudes. And so, like for instance here, if we look at figure 1, they say, okay, these are equivalent vectors. So they have a vector v and a vector u. Now, why are they equivalent? Well, the vectors both point in the same direction. Okay, so you have like the beginning point, initial point A, and then you have the terminal point B on the one vector, and then the other vector, the second vector, you have the initial point C and the terminal point D. But then that gives you vector u. But vectors v and u are equivalent vectors because they point in the same direction and they have the same length. So the length of the vector is equivalent to like its magnitude. Okay, how much force? Okay, how fast is the wind? That kind of thing. So pretty intuitive. Let me know if you have any questions. I'm just kind of go through here a little bit. Hold on. Wait. Question. Yes. Sure. Yes, and who?
Sorry. Even though they're equivalent vectors, just because they have the same direction and magnitude, them being parallel to each other in space, does that have any significance?
Well, if the vectors have the same direction, they have to be parallel in space.
Okay, cool. Thank you.
You're welcome. Now, we want to combine vectors. That's important. It's important to be able to combine vectors. So, like for instance here, they have in figure 2, they have a vector AC, and the vector AC would be equal to the vector AB plus the vector BC. So when you add vectors, you add them tip to tail. So the vector AB, okay, the BC, that vector, the initial point of vector BC is the terminal point of the vector AB. So you can add AB and BC, and you'll get the vector that'll be equal to the vector AC. So that's how vector addition works. If we go down here a little bit, okay, you have what's called the parallelogram law, which just shows that you have a parallelogram on the bottom. The triangle of the parallelogram has vectors u and v, and the top triangle of the parallelogram has vectors v and u. But those two vectors v are the same because they point in the same direction and have the same length, and the same comment goes for the vector u. So v plus u is equal to u plus v. Okay, vector addition is commutative. Okay, so that's just called the parallelogram law. Who's maybe heard of that in a previous class? The parallelogram law with vectors. And if you haven't, that's okay. All right. Well, let's just kind of move forward here. Hopefully this is intuitive. Intuition is worth a lot sometimes. All right, scalar multiplication. Okay, they give a definition here. Let's go to an example, figure 7. So here, in this picture, they have a vector v. And you can see in figure 7 that 2v, well, how much longer is the vector 2v compared to v? How much longer is it? Does it look like?
Twice as long.
Oh, twice as long. Okay, that makes sense. Sure. Okay, that's right, Emma. And that's right, Mario. And what about the half v? If they compare the half v vector to the vector v, the half v vector looks like it's blank as long. It looks like it's half as long. Okay, all right. Very good. And then, okay, well, now the negative v, we have in the green vectors there are negative v. Well, the negative v vector, well, how's the negative v vector relate to the vector v? It's just going in the opposite direction. That's all. Yeah, the negative values reflect the v vector going in the opposite way. All right, so I mean, that's just scalar multiples of v. Okay, I mean, are there any questions on that? Let's see. We would think of it as a, I want to be a little careful here. I guess a reflection about the origin. That's how we would think of it, Mario. When you have a vector and then you take the negative 1 of that vector, it's a reflection about the origin. Yeah. You're comfortable, Mario? Okay.
I'm good. I was confused trying to do the raise hand function, but thank you, Professor.
Okay, you're welcome. You're welcome. Okay, so, you know, just kind of, hopefully everybody's comfortable. Let me know if you have any questions. Okay, now, you know, we can add vectors, but we can also subtract vectors. But how would we subtract vectors? Here you have a vector u minus v. Well, we have to think about addition. U minus v is equal to u plus negative v, right? So we can treat subtraction of two vectors as the same as adding two vectors. Of course, the one vector is a negative vector. So in the picture below, they draw the vector u minus v. So what they've done is they've drawn the vector u, and they've drawn, so like on figure 8, okay, figure 8a, they've drawn the vector u, they've drawn the vector v, and then they've drawn the vector u minus v. Well, u minus v is the same as u plus negative v. All right, so do you see that, how that, if you take the vector u and add it to negative v, you get u minus v.
Professor?
Yeah, so, yeah, are there any questions on that? Yeah, oh, yes, Hyunwoo.
How are we connecting the point to the tail for whenever, for figure 8a?
Okay, I'll tell you what, let me show you here. Let me go to the whiteboard. Let me go to the whiteboard. I understand, that's a good question. Okay, so what I'm going to do here is I'm going to, you know, try to draw figure 8a like they have it. Okay, so here's a vector u. And by the way, in the book, when they use bold symbols, bold means it's a vector. But you denote the vector here with this vector symbol. So I know sometimes vectors are denoted like this, but that's not a good notation for this class. You want to use the arrow symbol. All right, so I'm drawing the vector u in blue, and I'm going to draw the vector v in green. And what we're interested in, of course, is the vector u minus v, which equals, by the way, u plus negative v. So what I can do here is the negative v would just be this vector, right? That would be negative.
Oh, Professor,
Yeah.
I think that the answer that I asked you can be addressed through figure 8b then, right?
Well, and what I'm going to do is I'm going to show you here. Good. So watch this now. Watch this. So the vector u. So this is like figure 8a in the textbook, but you see here how okay, you agree that this is u also because it has the same, this vector has the same direction and magnitude as this vector, so they're equivalent vectors. And so if I add u with negative v, that's going to be just an, hold on, that's going to be this vector. That is equal to u minus v. So in figure 8a, they show this red vector and they have u minus v by it. And that's why. They didn't show this part here, you know. But, you know, it's so now let me go back to the application, or back to the figure. And remember, you can use the zoom feature on the right if you want to blow it up. So now is that figure 8a a little better?
Yeah. It makes sense. Like you just translate u to another parallel area.
That's right. That's exactly right. All right.
Why would but for figure 8b, why haven't they just shown?
You know, I'm not worried too much about figure 8b. If you're good with figure 8a, you're gonna be good. Well, in figure 8b, of course, that's not a good educational answer, right? Figure 8b, what they haven't shown you is the vector v. If you make it negative v, you know, then if you add u and the vector negative v, you'll get u minus v in 8b. They just kind of don't like write it out. But if you write vectors u and v on your paper, you'll see that u minus v is correct. You'll see that.
Okay.
All right. Good questions. So, you know, moving on, you know, just kind of giving you a guided tour here. Oh, components. So vectors, you know, vectors have components. So just like, they're like coordinates, okay? So you see here in figure 11, okay, the vector A has components A1 and A2. Well, it has coordinates. The vector A is drawn to the point with coordinates A1 and A2 in figure 11 on the left there. That's a two-dimensional vector. So the components of A are the A1 and the A2. So the way they write it is then in component form. There are different ways to represent vectors. You can use arrows, but well, no, we use arrows for vectors. But what I'm trying to say is the vector A, if you write out its components, you use that notation. The little, like, they look like less than and greater than signs. How many have seen that maybe in a class for a vector, that kind of notation? Okay, Marwin has, and Mario has, and Charles has. Sure. And then on the right, you have the vector A drawn to the point. We normally draw the vectors. If we just draw a vector, we normally have it come out from the origin, and then it's drawn to the point A1, A2, A3. So then there's how you denote the vector A in terms of that notation.
Do you by chance know what that notation is called?
I never even thought about it. I'm sure there's a name for it, but it's component notation, I guess. It's component notation.
All right.
Okay. Well, so now sometimes what we want to do is, I mean, let me ask you this. Let me go to back to the whiteboard, and let me hold on here. I'm going to draw an X and a Y axis. Okay, and I'm going to have here, let's see, I'm going to have a point A that, let me see, maybe be a little bit careful here. I'm going to have a point A that has coordinates, say, 2, 1. And then let's see. I'm going to have a point. No, let me do it like this. I'm going to have a point B that has coordinates 5, 3. And I'm going to draw this vector here. And I'll call that vector, hold on, got to take off the, I'll call that vector AB. Okay, and what I want to know is what are the components of vector AB. I mean, it has to have an X component and it has to have a Y component, right? if you had to sort of guess, if you had to guess a little bit, so Ian thinks the components are 3, 2. Okay, well, let's see. Let's see here. What if, hold on here. That's right, Mario. Good, hold on now, hold on, don't hit the clear button, for gosh sakes, don't hit the clear button. Hold on, give me a line and give me some color. Okay, so, okay. So I guess we could get the components if we, hold on. If we knew this distance here, well, what's that distance? What's that distance equal to? That's right, that's going to be 3. Oh, now 3 happens to equal what? How did we get 3? We went,
The difference in
that
x values.
yeah, 5 minus 2. Right. What about this distance here? What's that distance?
3 minus 1 equals 2.
Yeah. So it appears that the components of this vector AB are 3 and 2. And it seems then, it appears that, hey, if we want to get the components of a vector between 2 points, a starting point and an ending point, we just subtract the coordinates. We subtract the coordinates. Okay, and of course, this would extend to vectors of 3 dimensions as well.
Professor?
Yeah, yeah.
Real quick, would you mind just quickly putting the direction of each of the components for me?
Well, the vector points in this direction. This is the direction that the vector points in.
True. So that means 3 would point to the right and 2 points upwards for their components?
3 units to the right and 2 units up. That's
Okay,
right.
cool. Thank you.
From the beginning point, go 3 units to the right and 2 units up. And incidentally, we can write this also like this. We can write this as 3 times the vector I plus 2 times the vector j. How many have seen ij notation for vectors? That might be something you've seen. And yeah, well, we'll use it a lot here. Okay, okay. You're learning, you're learning. Oh, what would the what would the magnitude of the vector A be? What would the length be of that vector A be? Let's talk about that also. How am I going to find the length of the vector AB? Okay, you're saying it equals root 13. Okay, well, what special theorem can we use to find the length? Being that we have a right triangle here, if I want the length of the hypotenuse vector, Pythagorean theorem. So it seems then all we need to do is square the x component, square the y component, add them together, take the square root. and indeed we get the square root of 13. Okay, does that make good sense? And so what I'm going to do is I'm going to show you the book has then the kind of the formal definitions for, but you know, intuitively you'll understand why the definitions are true. All right, let me go to the book, and this is in the recording. This is in the recording. Let me go back to the book. It's just so beautiful, this math. It really is. So here, now they're doing it for vectors in 3 dimensions, but all you do, if you have a vector A and B, and you want to find, well, if you have a vector that starts at point A and ends at point B, then that vector, which we can call vector A, you just subtract the components. It also works in 3 dimensions. Naturally, it's going to work in 3 dimensions. And also, if you want to find the length of a vector, okay, well, a 2-dimensional vector or a 3-dimensional vector, you just square the component, you square each of the components, add them, and take the square root. Okay, are there any questions on that? Okay, so I'm trying to make this intuitive. I think just from my math experience, anytime I could make something intuitive, oh my goodness, it helped a lot. You know, I believe in understanding things, not so much remembering things, but understanding things. Because if you understand the things, the ideas, then you know you don't really have to remember, right? Okay, well now let me go to you know, they have a kind of a nice big example here, example 4, where they do a lot of operations on vectors here. So you know, you have a vector A and a B, and they want you to find the length or magnitude of the vector A, and then find all these different combinations of vectors. And I'm going to just let you look at that example 4, and hopefully, you know, hopefully it makes sense what they're showing there. Take a look at it. Okay, are there any questions on what you're seeing there? Is it intuitive? Who's feeling comfortable with what? Maybe give me a thumbs up in the chat if you're comfortable. Okay, thank you, Ariane. Thank you, Charles. Thank you, Noah. Thank you, Kino. All right. Well, thank you, Hunwoo. Appreciate it. Hunwoo, did I pronounce your name Hyunwoo? Is that correct? Hyunwoo?
Without the W.
Hyunwoo.
Yep, Hyunu.
Okay.
Yeah.
Okay. Very good. Very good. Okay, all right, well then let's move on. Let's move on. So, what else do we see here in section 9.2? Okay, well, of course, the vectors I, j, and k. Okay, now I don't know if you've seen these before, but these are what are called unit vectors. The vectors, these vectors I, j, and k. And those are the components. So the vector I goes along what axis? What axis is the vector I on?
X-axis.
The x-axis. Good, good. The vector j, what axis is that on? Good, the y-axis. And the vector k is on the z-axis. Very good, very good. So we call those standard basis vectors, and if you take linear algebra, Math 284, you're going to learn there's a lot of, you can have different basis vectors for three-dimensional space. But for our class, since this is the most convenient basis, I, j, and k, for three-dimensional space, we'll use that. And that means that any vector in three-dimensional space can be written in terms of I, j, and k. Okay, and they have a nice picture here in figure 17 of I, j, and k. Okay, and so now, what can we do here? Well, I'll point out here that the vector 1, -2, 6, okay, in terms of the ijk notation, you just write that as 1i minus 2j plus 6k. Two ways of saying the same thing. And in your homework, you'll have problems where you have to work with both notations for vectors. All right. Okay, let me go down a little bit. Now, something else that is of value here is, I'll just go right to the example here. Let's say, this is example 6, that you wanted to find a unit vector in the direction of the vector 2i minus j minus 2k. So that vector 2i minus j minus 2k, that points in some direction. And if you were to draw the vector that starts from the origin to the point 2, -1, -2, you would see what that vector looks like. These are the kind of things you can do in MATLAB. Okay. Now, the given vector has, well, we know how to find the length of the vector. We just square each of the components, add them, and then take the square root. So that vector is going to have length 3. But what we want to do is we want to find a vector that points in the same direction, but yet has length 1. So all we need to do is take the vector and divide by each of the components by the length of the vector. And that gives us what's called a unit vector. So if we take the vector and divide each component by 3, then the vector 2/3 I minus 1/3 j minus 2/3 k, that vector is going to have, it's going to point in the same direction as the vector 2, -1, -2, and it's going to have length 1. Okay, so that's called normalizing a vector. Sometimes we call that normalization of a vector. Okay, and it'll come up later on when we are going to talk about directional derivatives. All right. Now, of course, like I had mentioned, like we discussed in the beginning, vectors have applications. Vectors have applications. Okay, and vectors represent forces. They represent tensions. They represent velocities. So we want to look at an application involving vectors. And the book has here, it has an example 7, okay, where they have a problem with tension vectors. And what I'd like to do, I'd like to actually do my example, because my example will be helpful for one of your homework. Well, that's a good example, but I want to do my own example, because then you'll have 2 examples. Okay, so let me go ahead here and bring up my example. Okay. And after we do this example, I think I'll be able to give you a little time to work on your next homework. So let me give you a little time to copy this example down, and then we'll go over the solution. Okay. All right. Okay, I'm going to give you a little more time to get the example copied down, and then we'll talk about the example. Okay, so in this problem, all right, we have ropes that are 3 meters and 5 meters in length, and they're fastened to a holiday decoration that is suspended over a town square. Okay. The decoration has a mass of 5 kilograms, and the ropes are fastened at different heights, making angles of 52 degrees and 40 degrees with the horizontal. We want to find the tension in each wire and the magnitude of each tension. So these ropes are holding up this mass, and there's force tensions on these ropes. We want to find what those tensions are, what those vectors are, because the tensions are represented by vectors, and when we want to find the magnitude of the tensions. So what's really going to help us on this problem? What do we need to do? I mean, to help us do this problem. What do we need? A diagram. That's right, Marwan. We need a diagram. Okay. And all right. So let's look at a diagram. May I go to the next page? Does everybody have the example copied down okay? Okay. Okay. Well, so now I will tell you in WebAssign, you'll have a homework problem like this, and it actually gives the picture, which is nice. But let me show you the picture. Hold on here. Now, wait. One moment, class. That's not the picture hold on. No. Hold on. That's not the right picture. One moment. I'm going to have to scan. What I mean is, yeah, the picture's not the one I want. It's not quite right. So give me a moment. I'm going to keep the recording going. Let me just scan the document. One moment. Okay, one moment, class. Let me bring up the right picture here. That picture's not right. Hold on here. Take this down. So let me see here. Happens occasionally. See, with remote teaching, if I were in the classroom, I would just, correct the picture. But it's going to be much easier here to have the right picture up. So, okay, there we go. Continuing on, this is the picture. So again, let me just, so we're connected here. We're doing this problem, and here's the picture that we need, the diagram. So, all right. So here's the holiday decoration. I've just drawn it like, you know, I could have drawn a star or something, or I don't know, whatever, you know, but I'm just drawing it as a dot. And it's anchored here and here. Okay, it's anchored at those points. And the tension vectors let me see here, are right there. So in other words, the hold on, Marwan, what no problem. So the weight is the holiday decoration has a mass of 5 kilograms, and so you know, there's the holiday decoration here, right? Hold on, I got to get that. The force acting on the holiday decoration goes downward due to what? Due to what? Why is the force acting on the gravity? That's right. That's right. So to keep the holiday decoration from falling to the ground, you need two opposing forces, and these are your tension vectors. So the tension vectors have to point in these directions. Now, you'll notice that the tension 3 vector is shorter than the tension 5 vector. Why would that be? Why am I drawing the tension 3 vector shorter than the tension 5 vector?
There's less tension in the shorter chord.
Well, it has to do with the meters. Okay, so Mario, the one rope is 3 meters long. Okay, and that would have to be then this rope here. Gosh, I got to get that. That would be this rope here, and then the other rope is 5 meters long. That would be this rope. So the meters corresponds to the length of the vector. Hold on. I might have said that wrong. One moment. No. Wait. Hold on. One moment. Well, yeah. The one rope's longer than the other rope. Okay, so the tension vector would be longer. So far, are we good, class? Are we good? I forget what I said about magnitude. Forget that. Okay, so now what we have to do is we want to figure out what the tension T3 vector is and what the tension T5 vector is. The T3 vector, we're told, I mean, the 3 meter rope makes an angle of 52 degrees with the horizontal. Okay, so let me just kind of, so here's that 52 degrees right here. with the horizontal. But then that means by the fact that you have alternate interior angles, if you remember your geometry from your high school days, this angle down here has to be 52 degrees. And similarly, the other rope, which makes 40 degrees with the horizontal, by alternate interior angles, this angle has to be 40 degrees. Okay, and so this is going to help us find the components for these tensions, because the cosine of, well, let me do the cosine of 52 degrees. Okay, cosine is defined as adjacent over hypotenuse. So this right triangle here, the adjacent side is, well, it's going to be negative x. Okay, because we're I want to say this the right way. Hold on here. Hold on. One moment. One moment. One moment, class. Yeah, so yeah, the cosine of 52 degrees is going to be negative x, which is the adjacent side, over the hypotenuse, which is the length of the third tension vector T3. And the sine of 52 degrees is opposite over hypotenuse, and that's going to be the y distance, which is y divided by the magnitude of T3. And so the vector T3 is going to equal xi plus yj, okay, xi plus yj, and that's going to equal then, by virtue of this equation here, x is going to equal negative times the magnitude of the T3 tension vector times the cosine of 52 degrees. That's going to be the component for the I vector. And then for the J vector, well, the sine of 52 degrees is y over the magnitude of T3. So y is equal to the magnitude of the T3 tension vector times the sine of 52 degrees. So the components of this third tension vector, the x component is negative, but the y component is positive. Okay, and so there you go. I mean, are there any questions on that? And of course, we're not done yet. We're not done yet. We can do the same analysis for the T5 vector. So in other words, the T3 vector, hold on, let me write it here. The T3 tension vector is equal to this expression on the right, and the T5 tension vector is equal to this expression on the right. I mean, are there any questions with what you see there?
Wait, where's the expression for the T5 vector?
Well, the T5 vector, I skipped a little bit of work, but if I were to put in the work there, the cosine, hold on, maybe I'll get my stylus. The cosine of 40 degrees would equal x over the magnitude of T5. But this x now is not, it's not this x, okay? It's a different x, okay? It's this distance here. And then the sine of 40 degrees will equal y divided by the magnitude of T5. But that's going to be this y here. The x is already positive. So in other words, I don't got to worry about a net involving a negative for this T5 vector, because T5 vector has positive x and y components. So if I take the, if I solve for x here, x would equal then, based on this equation, the cosine of 40 degrees times, sorry, the cosine of 40 degrees times the magnitude of that T5 vector. And then based on this equation here, the y component would be the sine of 40 degrees times the magnitude of the T5 vector. So I left that out just because I didn't want you to have to copy more than maybe you needed to. But there it is. You know, there it is. Okay, and so what I have to do if I want to figure out, okay, if I want to figure out what these T3 and T5 vectors are, well, if I want to figure it out, right, I'm gonna have to solve. I'm gonna have to find the magnitudes of the T3 vector and the T5 vector. If I could just find those magnitudes, I would, if I could get numbers there, then I would be good to go. So what we need to do here is we need to come up with an equation that will help us find those magnitudes. And you know, we have to make use of the fact that since the mass, the holiday decoration, it's in equilibrium, right? It's not moving, it's stable. So that means that the sum of the two tension vectors would have to equal the negative of the weight vector. Okay? In other words, the sum of all three vectors, the two tension vectors and the weight vector, has to equal the zero vector because it's in equilibrium. So therefore, T3 plus T5 would equal negative W. Okay, it would equal negative W. Now, what would that weight vector equal? Well, it's pointing downward, so there's no I component. It's strictly a J component. But what would the, well, it's strictly the J direction, but what would the component be? Well, you're going to take, well, you know, what am I doing here? You know, I got this 5 kilograms times 9.8 meters times 9.8 meter over s squared. What that's a force, right? Where am I getting that? Where am I getting that? You know, I just kind of put that there. Why is that a force? Think of Newton's laws. What's force equal to?
Mass times acceleration.
Acceleration.
Good Kino, good Mario. So I got a mass and I have acceleration. Oh, that's acceleration due to what? That 9.8 meter over
Gravity.
Acceleration due to gravity. Okay. So, well, that's just going to be 49J. Ian, I believe that I'd have to, that looks right, what you typed there. I'm always scared to answer too quickly. Okay, Charles answered for me. That's fine. Okay, well, all right. So it turns out then that T3 plus T5 is going to equal 49J. and 49j is equal to 0i plus 49j. And this is going to give us what we need to solve for the magnitude of the third T3 tension vector and T5 tension vector. Because what we can do is we can equate components. We can equate the components. I mean, when we add T3 and T5, okay, when we add the vectors, we combine the I components and the j components. So that means that this plus that, this plus that is going to have to equal 0 times I. And this piece of the vector and that piece of the vector, T5, when we add them, that's going to have to equal 49j. Okay? Does that make decent sense? So we need to solve for two variables, the magnitude of tension 3 and the magnitude of tension 5. Okay? And let me just see one thing here. The book calls it the length of tension 3 and the length of tension 5. That's fine. So we need to solve for two variables. We need two equations, and we have them. All right, may I go to the next page now? And are there any questions? Okay, so here are those two equations. Two equations and two unknowns. So now we can, you know, well, you know, we learned in Algebra 2 how to solve two equations with two unknowns. You can either add the two equations together and eliminate a variable, or you can do substitution. I'm going to do a substitution. I'm going to take the first equation and solve it for T5, the magnitude of T5. Hyunwoo, question?
Could you go back to that one page previous to this one, please, real quick?
Sure. We'll go, okay.
One second.
Okay.
Okay, thank you.
Okay, you're welcome. Okay, so here are two equations and two unknowns, and I'm going to do a substitution. I'm going to take the first equation and solve it for T5. And then I'm going to substitute that equation, substitute that expression in the second equation. Okay, which I've done right here. It's really beautiful, you know, and the book has a nice example 7. Sometimes they leave out a few details. You have to fill in the details. You know, that they assume at this level now you can fill in missing details. Of course, for exams, you want to have all the details, right, in your work. Hold on, that's this is T5 right here. And so we can factor a T3 out on the left, and then we have inside here we have sine of 52 degrees plus cosine of 52 degrees over cosine of 40 degrees times sine of 40 degrees. That will equal 1.3046. And I go out a fair number of decimals because WebAssign, I have a high tolerance setting for answers, like decimal answers, because I don't want WebAssign to mark a problem correct if you did it wrong. And sometimes what happens is if the tolerance limits are too lenient, you can do a problem wrong, but get an answer that's like close enough to the right answer that it marks it right, and then you think you did the problem right. And of course, we don't want that to happen. So the magnitude of T3, it turns out, will be 37.56 newtons. Okay. So, you have, in terms of forces, you have, like, for instance, if you had pounds, that's a unit of force, then your units would be like in feet. But in this problem, we have meters, and so forces are going to be in newtons, or the magnitudes are going to be in newtons. How many have seen newtons in other classes? That okay, Ian has, and Gordon has, and you don't have to be a physics expert here, right? You don't even have to have taken physics to really understand this. I mean, it helps a little bit, but you'll be fine. No matter what, so long as you've had calculus 1 and 2, that's what you need, right, to take this course. So, and you're going to learn a lot of things. But it's always nice when, things confirm things you've seen in other courses. So, okay, we know what the magnitude of the third, or the length of the third tension vector is. The magnitude or length is 37.56 newtons. And now what we can do is we can figure out now T5, because we know what the magnitude of T3 is. And so when you're ready, I'll move to the next page. Please let me know if you have any questions. Okay, Mario. Do you think you might see this problem on an exam, possibly? Would this be a good problem for an exam? Okay, Mario's thinking it's pretty close to 100%. Well, if you can do this problem, then you understand a lot about vectors, right? Okay, if everybody's good, I'll move to the next page then. Who knew? How are you doing? You're comfortable?
Yeah, I'm taking a bit to soak everything in, but I'm
Of course. Of course. Okay. Okay. Well, then let's All right, now we go to the next page, and again, here's the magnitude of that T5 tension vector. And now we're able then to figure out the actual vectors themselves for T3 and T5. Because we substitute in the magnitude of the tension vectors. All right, are there any questions at all? Okay, so now like for WebAssign, it might say, go out to 2 decimal places. And so, that's what I did here. But I forget honestly how many decimal places they want. But all right, well, if we're comfortable, I'll stop the recording then.